Hi, I'm going to present joint work with Michael Kearns and Emily Ryu. Before I begin, let me say a few words about Emily, who visited us at Penn this summer when this work was completed. Um, she was a really amazing, warm, energetic presence. It was a pleasure doing research with her. Um, she tragically died in the fall back at Cornell unexpectedly, which is why I'm giving the talk here. But this is her work. She should really be the one presenting it. She enjoyed it, and I hope I do it justice. Okay, so we're gonna work in a pretty standard machine learning setting. There's a joint distribution over features X and labels Y, and the labels are real valued, so this is a regression problem. And the twist is that there are different learning agents who are embedded in a network, in a directed acyclic graph. And each agent only sees a subset of the features. The view of each agent is limited. They don't see all of the features, but they do see the labels. And agents also observe the predictions made by their parents in the network. And so what they get at the time that they need to make predictions are the features that they directly that they directly observe and the predictions of their parents. And they make these predictions by solving some empirical risk minimization problem, some regression problem to minimize mean squared error. And they make those predictions, and those are in turn observed by their children in the graph. That's how information propagates in the network. So for example, if the hypothesis class is all linear functions on the input variables, then what each individual agent is doing is just solving a linear regression problem. Again, using as features the real features that are directly observed and the predictions that their parents made. Okay, now if a single party observed all of the features, then they could just learn the optimal linear regression function on the features. That's what we're gonna sort of compare ourselves to. And we're gonna say that a network aggregates information. If there's some agent, it'll always be a leaf agent, such that um, despite the fact that they were not able to observe all of the features, the accuracy they get, the mean squared error they get, is comparable to the accuracy they could have gotten had they observed all of the features directly. Okay, so we've got some arbitrary directed acyclic graph zooming in on a particular agent. The agent observes the predictions of their parents as well as their own local features. They solve some mean squared error minimization problem like a linear regression problem. They produce a prediction which then propagates through the network to their children. And we're going to look at agents typically, there are leaves in this network, and we're going to look at their mean squared error, and we'll say that the network has aggregated information if that mean squared error is comparable to the optimal model in the class trained on all of the features together. Now, there's other network learning models out there. Let me just briefly compare it to two styles. Um, One sort of popular model is called degroote dynamics. Here, every agent maintains some scalar or vector valued estimate of a state and just repeatedly averages that with its neighbors. And sometimes you might think that the estimate that each person starts with is some unbiased estimate of a true state. And people study conditions under which these degroote dynamics converge to agreement and to the true state. This is a very simple model from our perspective. It's too simple. At the other extreme, there's a literature that studies full Bayesian learning. There's some kind of, again, state that agents have a common prior over. They observe different observations, and they share with each other their full posteriors, and they do full Bayesian updates conditional on these posteriors. And again, people study conditions under which you reach agreement and information aggregation. But this is too complicated. In general, these dynamics are intractable. And what we're studying is some sort of machine learning inspired middle ground. Everyone's doing efficient empirical risk minimization. The distribution can be arbitrarily complicated, and we're going to compare ourselves to the best model in class rather than the Bayes optimal model. And the punchline of the paper, the TLDR, is that depth in the graph is both necessary and sufficient for information aggregation. We're not going to get information aggregation in general just from size, even if we have broad coverage over all of the features. Depth is necessary and sufficient. Okay, now for most of the talk, we're gonna focus on linear regression, although the paper is more general. And there's this really useful fact about linear regression, and it's the following. If I solve a linear regression problem over some class of features, then the model that I get out the end, F star, will have residuals that are orthogonal to every linear function over those features. So if I look at the expected product of any linear function of the features times the residuals of my model, that'll always be 0. Let's call this multi-accuracy with respect to linear functions. And if I'm solving linear regression, well, my model itself is some linear function, which means that the residuals of my model will be orthogonal to the predictions of my model. That's just a special case of the multi-accuracy statement above. Let's call that self-orthogonality. That's going to be really useful. Now, remember, each agent is going to solve a linear regression problem over their own features and the predictions of their parents. Okay, so let's think about the mean squared error of an agent's predictions, y hat. If you look at mean squared error, it turns out there's sort of a natural decomposition that's going to be really useful for us. The mean squared error of the predictions made by the parent will be equal to the mean squared error of the predictions made by the child, plus the squared difference, the expected squared difference between the predictions of the parent and the child, plus some cross term. And if you expand out the cross term, you get 2 terms. The first one is 0 because the solution to a linear regression problem is self-orthogonal. That zeroes out this first term. And the second one is 0 because the solution to a linear regression problem is orthogonal to any linear function of its features. And because the child used the parent's predictions as a feature, in particular, it's orthogonal to the parent's predictions. And when these cross terms zero out, what we get is that the mean squared error of the parent is equal to the mean squared error of the child plus the expected squared disagreement between the parent and child's predictions. So it's saying if you want the parents and the child's predictions to be nearby one another, it suffices that they have similar mean squared error. Now, this very simple statement has a whole bunch of useful implications. So the first is that because the expected squared disagreement of 2 predictors is non-negative, it means that if a predictor is multi-accurate with respect to some class of models, say all linear models, and self-orthogonal, then the mean squared error of the predictor has to be at least as low. The model has to be at least as accurate as the best model in this class, H. Okay, that's going to be useful for us. It also means that if you look at the mean squared error of any sequence of agents that lie along a path in this graph, that has to be monotonically decreasing, again, because the squared disagreement has to, is non-negative. And because of that, if you look at a long path of agents and just think about how their mean squared error has to evolve, well, it's monotonically decreasing, as we just observed, and mean squared error is bounded. Say the labels are, numbers between 0 and 1. The mean squared error starts off at most 1. It can't go below 0, and it's monotonically decreasing, which means that if the path is sufficiently long, there have to be long periods in which the mean squared error is stable, right? It can't for very many rounds decrease substantially before it becomes negative. So mean squared error has to stabilize along long paths, not forever, but at least for long stretches. Now, because we have this decomposition that says that the expected disagreement between an agent and its parent, and any parent in a path, is exactly equal to the difference in mean squared error, it means that when we have long stable paths, long paths in which the mean squared error isn't decreasing much at all, it actually implies stability of the predictions. If the mean squared error isn't decreasing much at all along the path, then in expectation, the predictions of every agent along the path have to be almost identical. Along stable paths, adjacent agents must make very similar predictions. And remember that a consequence of squared error regression is that each agent will be multi-accurate with respect to linear functions of their own features. But if my predictions are almost the same as your predictions, you're my parent, and your predictions are multi-accurate with respect to linear functions on your features, then my predictions have to be approximately multi-accurate with respect to linear functions on your features as well. Okay, and more generally, if mean squared error and hence predictions are approximately stable along this whole path, then the final agent in this path has to have a predictor that's approximately multi-accurate, not just with respect to their own features, linear functions on their own features, but with respect to linear functions on all of the features that were encountered by anyone along this path. Okay? Just because everyone's multi-accurate with respect to linear functions on their own features, and that transfers across agents if the mean squared error and hence the predictions of the agents are almost constant along this path. So finally, putting it all together, since multi-accuracy and self-orthogonality imply accuracy, what this means is that if we have a stable subpath containing agents that collectively span all of the features, we have to have aggregated the information by the end of the subpath. And sufficiently long paths have to guarantee very long stable subpaths, just because error is bounded and monotonically decreasing. And that's morally how we get this theorem. If variables are distributed such that with high probability, every subpath of length m spans all of the variables, then if there's any path in the graph that has size on the order of m over epsilon squared, that suffices for epsilon approximate information aggregation. In particular, if the features are distributed randomly in IID, m is on the order of log d, so the paths don't need to be that long. Now, just mentioning the generalizations in the paper very briefly, I described to you the linear case in which everyone is running linear regression. But we only use two properties of linear regression: the fact that it has this self-orthogonality and that it achieves multi-accuracy with respect to some hypothesis class, in this case, just linear functions on the local feature space. Well, more generally, gradient boosting over arbitrary hypothesis classes guarantees these properties with respect to these arbitrary hypothesis classes. And so this lets us recover similar statements without assuming linearity over arbitrary hypothesis classes, where the comparator is to the best predictor in the span of the individual agent classes along any stable path. Okay, and I don't have time to talk about them, but there exist lower bounds as well. So the upper bound told us that information aggregates over paths that have length at least m over epsilon squared. We can show that length at least m over epsilon is necessary. And in fact, there are distributions such that no matter what the topology of the graph is, information aggregation fails to happen if the graph is not sufficiently deep, altogether telling us that it is depth and not size that governs information aggregation in the worst case. And that's it. I can't answer questions, but I want to take a moment just to hold Emily in the light. Thank you.